Hello everyone, I welcome you to this online tutorial class. My name is Mr Uche1 and I'll be taking you on the topic fundamentals of motion in physics. But before we dive into what we have in fundamentals of motion, let us quickly look at our objective of this particular topic. Okay, by the end of this session, we should be able to understand the concepts and define motion. Then we should be able to list out the types of motion as well as differentiate them from the others. There are some motions, some thin line between some certain motions we should be able to distinguish at the end of the day of this class. Introduction to kinematics, terms used in the study of kinematics. Next is the scalar and vector quantity concept of bearing. The scalar and vector quantity concept of bearing are key elements for us to understand distance and displacement, as well as speed and velocity. Then finally, we are going to move into equations of motion. So let's quickly go into the introduction of motion. What comes to my mind is movement, change in position. Okay, but you understand that motion is a very important topic in classical mechanics, and you also agree with me that everything in the universe is always moving. Even while you're on earth, you tend to be still, you seem to be still, you seem to be stationary, but you are still moving. As long as the earth itself is moving, you are still moving. In our day-to-day activities, we have objects moving from one point to another point. Okay, so with this, you can find that there is a change in position of these objects, but then with respect to time. So if you are to define the term or the topic motion, it is defined as the change in position of a body with respect to time. So it involves how things move from one point to another. And of course, what comes in again in mind is what actually causes the change of this position of body in time. And of course, you agree with me that there is always a force, there's always a physical agent which is referred as the force that changes this body from one point to the other. So this now brings us to the study of motion, which is studied basically based on the force that causes this motion. Okay, the study of motion is classified into two. We have the kinematics and we have the dynamics. The kinematics, here we study motion without making any reference to the force that causes motion. But in dynamics, we make reference to the force that causes motion. But in this particular class, we are going to dwell more on kinematics. And as we move into the kinematics, you see that it has several branches, several aspects. So we are going to concentrate in a particular concept in the course of this particular study, which I will reveal to you as time goes on. So let's move to the next, which is the types of motion. Types of motion. Now we have basically 4 types of motion. We have the translational motion, we have the oscillatory motion, the random motion, and the rotational motion. Now let's take them one after the other. Translational motion. What then is translational motion? Translational motion is the motion or the movement in which all parts of the body moves uniformly. All parts move uniformly. All points of the body move uniformly in the same direction. Okay, so if an object is set into motion, into a translatory motion, into a translational motion, as the object moves, there is no change in the object's orientation. All points in that object move along uniformly towards that path. Now, in a perfect translational motion, the particles, every of the particles are always in parallel to each other. That means there is no change in the rotation of their movement. They move parallel to each other towards a particular direction. The translational motion is divided into two. We have two types of translational motion, or we have they are classified into two. We have what we call the rectilinear motion, and we have what we call the curvilinear motion. When you have the movement of a body such that all the parts of the body, all the particles of the body are moving uniformly in one direction along a straight line, then that translational motion is referred as what? Rectilinear motion. But when you have a situation where all parts of the body are moving uniformly along a curved path, then we refer it as what? Curvilinear motion. Example of rectilinear motion, we have a car or a train moving along the road, as we have it in the slide here. A girl sliding down a slope is as well a rectilinear motion. A boy that is undergoing a 100-meter race from point A to point B, okay, is as well undergoing a translational motion. Of course, rectilinear in this case. Firing off a gun from a bullet as well. So the next is what? The oscillatory motion. The oscillatory motion, of course, the to and fro movement, the repeated to and fro movement about a fixed point. One, there must be a fixed point, and the bodies go repeatedly, to and fro repeatedly, okay, along the same path. Okay, most times the people say that okay, the oscillatory motion can as well be referred as the vibratory motion. Of course, sure, they can be referred as the vibratory motion, but there's a thin difference per se, not actual, but it's good we simply just distinguish them a bit. The oscillatory motion, of course, is a slow to and fro movement, a slow to and fro movement about a fixed point. But for vibratory, it's very fast. That goes to and fro very, very fast. For instance, the piston in car engines, it goes like that, very fast. That we refer as vibratory motion. For instance, when you tap or a plucked guitar string, okay, the plucked guitar string, when it is plucked, the guitar goes the oscillation is very fast. It goes, very fast. The frequency is so fast. So that I can refer as vibrational motion. Okay, but they are all in the same motion, which we call the oscillatory motion. But the vibratory seems to be faster, while the oscillatory is slower. Okay, so example of the oscillatory motion, we have the vibration of a plucked guitar string. We have motion of a pendulum as it is swings back and forth. Then vibration of the molecules of solids, the to and fro motion. Okay. Then we have the next, which is random motion. Random motion. Okay, haphazard movement of objects haphazardly in a disorderly manner. Okay, goes to changing directions. Directions. But you should understand that this direction they change, they move straight translational, hits an object, or perhaps change direction again, translational, change the other direction again, like that. Okay, so a typical example of this random motion, we have the motion of gas molecule. We have liquid molecules. Motion of gaseous and liquid molecules. We have the Brownian motion of visible particles. Then we have an insect flying, a bat also flying. So they are all random motion. But let me just emphasize on this Brownian motion. Okay, now you should understand that it is not all random motion that could be Brownian motion, because when you look at the definition of Brownian motion, it is the rapid irregular movement of tiny particles, microscopic particles, due to the bombardment of the fluid in which they are suspended in. Okay, so that is Brownian motion. But you find that an ant in search of food, an ant is not microscopic. Do you know that even a man or a woman in a crowded marketplace, moving around the crowded marketplace, performs random motion, but that man or woman in the marketplace is not microscopic, is not tiny. Okay, so random motion is basically emphasized on tiny particles suspended in fluid, okay, of which the random motion in there is as a result of the bombardment of the molecules of the fluid on those particles. Okay, so now let's move to the next one again, which is rotational motion. Under rotational motion is a type of motion whereby all points in the body move in concentric circles about an axis. Concentric circles about an axis. For example, we have the rotation of the earth about its axis, rotation of blades of a fan, the turning of a tap while opening or closing it, turning of steering wheel, and even the movement of the tires of cars. They are all rotational motion. But then let's draw a thin line between this rotational and circular motion. Of course, they're within the same the same family, the same umbrella. But then let's just draw a thin line between them. Now, for circular motion, they are talking about, for both of them, they have to move about a fixed axis. But for circular motion, the axis about which they move is out of the body, is not within the body. It's not within the body. For instance, you have a car that moves round a roundabout. Okay, the axis is at the middle. Okay, and the car moves round it. That I tend to be circular. But when you talk about rotational, okay, the body goes round like the earth. It goes round, but then its point of axis is within its body. Okay, rotational within, the point of axis is within its body. But for circular, the point of axis is out of its body. All right, now let's now move. Earlier on I said that our basic aim for today is to discuss the kinematics. Having known what the types of motion and what causes motion, of course we said force, we don't want to treat force extensively, maybe some other time. Then let's talk about the study of motion, which is divided into two. They are the kinematics and we have the dynamics. Now, both kinematics and dynamics jointly are parts of mechanics. Mechanics, which is a branch of classical physics. Okay, and this mechanics is as a branch of physics focused on motion of objects and forces that causes the motion to change. And of course, here we talk about motion and force, all studied under mechanics. But then we classify it kinematics, where we do not involve the force at all that causes motion. Then dynamics, we involve the force that causes motion, that changes that body. Okay, but in our subsequent video, we are going to discuss dynamics. But today we talk about kinematics. But we are going to still streamline the aspect of kinematics today into one-dimensional motion, one-dimensional linear motion. That is our aim, what we are going to discuss today. Actually, we can discuss kinematics under one dimensional motion, okay, horizontally and vertically. Then we also as well discuss it in two-dimensional motion, which has to do with the projectile motion. But today we are going to streamline the study of kinematics into one-dimensional motion. And in that one-dimensional motion, perhaps we are going to discuss only horizontal linear motion. Okay. Now, as you can see in your screen, we have the kinematics deals with the concepts that are needed to describe motion without any reference to force. Dynamics deals with the effect that forces have on motion. Okay, still on kinematics. Now you agree with me that there are several aspects that we use to describe kinematics. Okay, in science, for us to understand kinematics, we have several tools that we can be able to use to describe kinematics. We have some tools we use, such as the words, that's terminologies that we can use, which I'm going to meet later. We have diagrams, we have the graphs, we have equations per se. But today we are still going to streamline our discussion more into what words and equations. Okay, right. The goal of kinematics is to develop mental models to describe the motion of real world objects. Okay, to describe the motion of real world objects. We will learn to describe motion using the words, as I said earlier, diagrams, graphs, equations. But we streamline today's online class using the words, which are the terms needed in the study of kinematics, and the equations that should be applied, okay, at constant acceleration and at constant speed and thereabout. So so what are these words we can use to describe motion? Now, if you look at in our day-to-day activities, normally to a layman can use several words to describe motion, to describe movements. Okay, every person without a background in physics has a collection of words which can be used to describe moving objects. For instance, one can say, okay, stop, slow down, okay, the vehicle is speeding up, returning provide a sufficient all these things provide a sufficient vocabulary for describing motion of objects. Okay, even at the point you can say that something moves very fast as well. Those are the words that can be described, that can describe motion to a layman's in the layman's terms. But in the study of physics, we have some particular terms that we make use of. And what are these terms? Okay, these are the language of kinematics. So what are these language? We have the distance and displacement, which I'm going to distinguish them. We have the word speed and velocity, and we have acceleration. Distance and displacement, speed and velocity, and acceleration. Okay, now we are going to discuss about these languages, these terms which we use to describe kinematics. But we are not going to understand this very well without us looking at some of the tools that we can use to explain distance, displacement, speed, velocity, and acceleration as well. So we need to understand some certain concepts for us to be able to have a well understanding of those terms used in the study of kinematics. And what are these concepts? What are these tools that will aid us in studying in understanding these terms in study that is used in study of kinematics? Now we have the first one we talk about is scalar and vector quantities. Okay, scalar quantities, vector quantities. So what are scalar quantities and what are vector quantities? Okay, listen to this illustration. The boy walks 20 meters. Then the other illustration, the boy walks 20 meters towards the market. The boy walks 20 meters. The boy walks 20 meters towards the market. Now, in the first case, I only mentioned the magnitude, the size, the amount of distance which the boy has walked, and that is 20 meters. But in the other illustration, I also included the direction which the boy was walking towards. So the boy walks 20 meters, only describe its magnitude but no direction. So we refer that as a scalar quantity. Then the boy walks 20 meters towards the market. The boy walks 20 meters towards north. The boy walks 20 meters due east. Indicates the magnitude and as well as the direction. So we refer that as a vector quantity. So a scalar quantity are quantities which are described by a magnitude only magnitude. Whereas the vector quantities are quantities which are described by both magnitude and directions. Now, if you look down here, we have a couple of examples of them. A couple of examples of scalar quantities, vector quantities. Then it should interest you to know that vector quantities are represented by what? By lines. Okay, we use the line to represent vector quantity, then the arrow head to indicate its what? Direction. Actually, I will not go too deep into scalar and vector. This alone is enough for us to understand the basic idea of what distance and what displacement. Okay, now the example of scalar quantities, we have them: length, area, speed, mass, distance, and so on. For vectors, we have displacement, velocity, acceleration, and so on. But then there is a little a particular way I always use to identify scalar and vector each time, because I don't cram them. I usually have some ways which I do what I do identify them. Actually, it works in most physical for most physical quantities. Now, if you look at what I have here, just as we have like charges, or what we have on your positive to give you positive, negative gives you positive, negative gives you what? Negative positive gives you what? Negative. So let's take scalar to be what? Positive, and vector to be what? Negative. So if we have what? Scalar times scalar, or scalar divided by scalar, it gives you scalar. You have vector times vector, or vector divided by vector, it still gives you scalar. That means you have both of them the same, alike what quantity, scalar, vector, either they are being multiplied or being divided. The resulting answer to that quantity is going to be scalar. Now, when you have different them differently, scalar times vector, or scalar divided by vector, or vector times scalar, or vector divided by scalar, the resulting answer is going to give you vector. So let us try it here. The example we have here, we have walk. But before then, there is a way you need to know. You should be able to know the definition for several physical quantities. Okay, like for instance, work. What is the definition of work? What is the formula for work? Work is force times displacement. Okay, of course, most of us is force times distance. If you don't say force times distance, you will not get it right. You have to complete the definition. Force times distance move in the direction of the force. So it's in displacement, direction of the force. So force times displacement. Force is a vector, times displacement is a vector. So vector, of course, will give you what? Scalar. So that means work is a scalar quantity. Let's try it in the case of moment. What is the formula for moment? Moment is the product of force and perpendicular what? Distance. That is force times distance. Force is scalar or a vector? Force is a vector. What about distance? Distance is a scalar. So when you have vector, scalar, what then will it give you? They are both different. So vector, scalar. So definitely it's going to give you what? It's going to give you a vector. It's going to give you a vector. Okay, so you can try that for several what? Physical quantities. You can try that for what? Momentum. You can try that for impulse and some other. All right. As I said, it works for most what? Physical what? Quantities. Okay, so next is the concept of what? Of bearing, which is a very important tool in understanding what distance and what displacement. Now, the bearing of an object from the origin is the angle which it makes with the North Pole in the clockwise or sense. That means from the north, it moves in the clockwise direction. That is the bearing. And we have two ways of representing what bearing. We have the cardinal what point bearing, and we have the three-digit notation, the three-digit what notation. In the cardinal points, we have the north, south, west, east. Then we have the northeast, if you are moving in the direction of what? East. We have the northwest, if you are moving in the direction of what? West. We have the southeast if you are moving in the direction of the east, and we have the southwest if you are moving in the direction of south. Please, we do not say west, north, or east, north, or west, south. No, it is southwest, southeast, northeast, northward, west. Okay. Now, for instance, let's look at the one we have, the example we have here. In the example, here we have not 40 degree what? East. So this is a cardinal what? Bearing. And over here we have south 75 degree what? West. Then if you come to the three-digit what? Bearing. In the three-digit bearing, you can see that from the north there's a direction clockwise down to where the line of the of that angle is. And if you look at it, what we have there is 160 degree. Then the other side we have 40 degree, which is also three-digit bearing. But what is different between the three-digit bearing you have here and the cardinal bearing method which we have at the top there, which we have at the top? at the top here. Now at this particular one here is not 40 degree what is. When we come to this point 40 degree, you can see that you have 3 digits here, 0, 4, 0, indicating that this is your what? This is 3-digit what? Notation. So for all 3-digit notation, that must be in 3 digits. Now for this other one, in the you have south 75 degree what? West. 75 degree what? West. This is what the cardinal what Deriving method. Then if you have to change this other one to give you a what? A 3-digit notation, that means from this end comes here, because all 3-digit notation begins from the what? North and moves clockwise. So it comes this way. Here I have what? I've gone through 180 degree. Then this end here is 75. So what then would it be? 180 plus 70 what? 5. 180 plus 75. I think you should have like 255 degree. 255 what? Degree. Fine. That is your 3-digit what? Notation. So now, having discussed these 2 key tools, now let us dive into distance and displacement proper. Okay, so what then is distance and what then is displacement? Let's begin with distance. Distance refers to the total length of travel irrespective of the what? Of the direction of the motion. Okay, so basically distance deals with the path followed. The path followed by the what? Object, irrespective of the what? Direction. But when it comes to displacement refers to the distance moved in a particular direction. It is the object's overall what? Change in position. The overall change in position, which simply means that what? To obtain the displacement, okay, the overall change, that means it should be the distance, the direct distance from the starting point to its end what? Point. It does not actually refer as the path followed, but its distance from the beginning, the shortest distance from the starting point to the end point, which we are going to what? Explain further in the next one video. So distance here is a scalar quantity, and displacement of course is a vector quantity. Why is displacement a vector quantity? Displacement is distance moved in a particular direction. That is direction there, but something is common between them, and what is that? They both share the same what? Units. Their SI units are both in what? In meters. So to understand the concept of distance and displacement further, let's go to the next slide. Okay, now looking at this and this point, yeah, okay, if Mr. A boy moves from this end to his house, okay, from this point, this tree, down to his house, and after which he decides to go out again to pluck some fruits, and instead of coming down here again, he moves from B down to what? C. Okay, let's take the movement again. From A he moved to P, to his house, dropped his bike, then from B moved down to what? C. Okay, now the question is, he started the journey from A, moved to B, then from B down to what? C. So what then is his distance? What distance did he cover? He started from this point, moved 4 meters to B, and from B down to C, meaning that what? He has covered what? 7 what? Meters. That is A to B 4, then what? B to C 3. So the distance covered by this boy is what? Is 7 what? Meters. But when you talk about its displacement, the displacement, of course, as long as there has been a change in this direction, his displacement, of course, is the shortest distance, that the shortest path followed from his starting point to its what? To the end what? Point. This is the starting point, this is the end point. And what is that shortest distance which you can create here? It is what? It is this line down. So if this is meant to be a right angle triangle, of course, what are we meant to apply here? For a right angle triangle, we have applied what? The Pythagorean's what? Theorem to obtain this what? 5 meters. When coming to this point here, okay, let's look at it this way. You have a man from this starting point here, he moved what? 5 feet from this end down to this point here, and he now moved 5 feet again back again to that same point. Let's take it again. From this is the starting point, he moved 5 feet down, then 5 feet what? Back again. So let's analyze this together. So what is the distance moved by this man? No, let me say a girl this time, not a man. This was a boy. Let me take this to be a girl. Yeah, the girl moved 5 feet down here, then from this point, and that 5 feet down again. So what could this about is what is the distance moved? The total distance moved, or the distance moved by this girl, is 10 feet. 5 here and 5 here. Distance deals with the path followed. But then what is the displacement? For you to understand displacement, just have in mind that it is the distance, shortest distance from the starting point to the end point. So where is the starting point at that same position? And where is her end point rather? Her starting point is that 5, this point here, and her end point or her finish point is still that same point. So is there any distance between these 2 points? Of course, the answer is no. So your displacement at this point is what? Is 0. All right, let's take some good example here. Example, we have the first example we have here will give us a good understanding of distance and displacement. The question says a boy walks 20 meters eastwards. Then, okay, wow, this kind of mistake here. Should be then typographical error. A boy walks 20 meters eastwards, then 40 meters northwards, and later 50 meters west. Number 1, determine the total distance traveled. Number 2, displacement of the boy from its starting points. Okay. Then number 3, average velocity of the boy afterwards. If the entire journey took 50 minutes, then there's average speed after the same time. So let us take the first one. First is the diagram. Let's get the diagram. The diagram begins from this point A. Okay, first if you have to sketch this, you put your 4 cardinal points here. The cardinal points. Then have a cardinal points here. Then it says it move 20 meters eastwards. So this is the east. East is this direction, 20 meters. Okay. Or getting to this 20 meters, we now have then 40 meters northwest. 40 meters northwest. In reality, this 40 meter, the length of this of 40 meters should be longer than this because we are dealing with vector. Okay, the magnitude indicates the length indicates magnitude. The longer the line, the greater the magnitude of that particular vector. So in this sense, this 40 meters is meant to be longer than this 20 meters. But let us continue to get a good understanding of what we are saying here. Now, at this point, what happened again? Later, 40 meters west. So from this particular point, this is my west. It moves west. Okay. Now this, of course, this line is okay. 50 meters, which is very long, indicating the magnitude of 50. So this is your starting point, and here is your end point. Your starting point A, it went 20 meters, 40 meters north, then 50 meters west. Starting point, end point. So let's answer our questions. Number 1, determine the total distance traveled. How can we obtain the total distance traveled? Remember, in my previous slide, I told you that distance is the path followed. The path followed. So let's look at the path followed in this case. From A to B is 20. Then from 20 down to C, that is 40. Then 40 down from C down to D is 50. So what then do we do? 20, 40, 50. We add them up. 20 plus 40 plus 50. Everything gives me 110 meters. So that is my total distance traveled. But when it comes to displacement as I earlier explained, is that shortest distance from the starting point to the end point. Identify your starting point, identify your end point. This is the starting point A and this is the end point D. Okay, so if I draw this line up down here, straight down, okay, I'm going to have a right angle triangle. So from this point here, A, to this particular point, what is the distance? The distance corresponds to the distance from B to C, so this is 40. Then what about this point to D? If the entire point from D to C is 50, and from A to B, which corresponds from this end to C, is 20, so it means that from D to this particular point here is 30 meters. So here is 30, here is 20. So since it's the right angle triangle, what then will I do? this should be okay, this should be 40. Here is 40. From here to here is 40. Here to here is what? 30. So 40, then here is what? 30. So since it's the right angle triangle, what then should I apply? I apply the Pythagorean's what? Theorem. Okay. So to obtain the hypotenuse, which is the displacement, apply your what? Your Pythagorean's theorem, then which is 30 was square plus 40 square, all roots. Then at the end of the day, you have what? 50 what meters. So 50 meters is the displacement of this young boy. Now, how did we obtain the average velocity? The average velocity, total displacement over the total time is my average velocity, of course, which is total. How do I obtain the total displacement? Is what we have here in the previous. Okay, displacement is 40, distance is 100. So we come over here and we substitute. My total displacement is what? Is 50 times what? 15 times 10. Why 15 times 10? Let's go back and see. Okay, the time is what? Is 15 what? Meters. No, 15 meters. That is a little. No, it shouldn't be. It shouldn't be. Okay, this is 15. It means that what? No, this should be 15 times 60. 15 times 60. Okay, 15 times 60. So 50 all over 15 times what? Times 60. Then you find your final answer. The same thing, total distance is 110. Okay, then the time taken for that same time is what? 15 times what? 60. Okay, it's typographical error right here. Okay, now let's move down to what? Speed and what? Velocity. The speed and the velocity. Okay, speed. Yeah, the speed is the rate of change of what? Distance. It is a scalar what? Quantity, and the speed is equal to the distance traveled over the total what? Time taken. We have several forms of speed. We have uniform speed. Uniform speed is when the change in the distance is moving at equal rate. Equal rate in the change in time. Equal change in time interval with equal change in what? In the distance traveled. All right. We have non-uniform speed when there is the rate in change of distance is not at equal time interval, so it is a non-uniform what? Speed. We have the instantaneous speed, which is what? The speed at an instant of what? Time. So we also have what? The velocity. Velocity is what? Is the distance traveled in the what? Specify what? Is the rate of change of distance traveled in the specified what? Direction. The rate of change of distance traveled in the specified direction, or you can say that it is the rate of change of displacement. Velocity is a vector of what? Quantity. Okay, then velocity, the formula is change in what? Displacement over what? Over time. Okay, now there's something we need to know about speed and velocity. At times we do interchange. We do use speed in terms of what? Velocity, and velocity in terms of speed. But you should know that speed and velocity are not always the same. They don't have the same what? Value. They do not have the same value. But most times when we say the speed is 260 meters per second, velocity as well is 260 meters per second. In this case, they are in the same direction. If the object is moving in the same direction with that same speed, so definitely the velocity will also have the same what? Magnitude, the same value as that of the speed. But once there is a change in direction, the speed and the velocity will be what? Will be the same. But if they have the same value, okay, so at that point the speed and the velocity are moving in the same what? Direction. So that is what we have here. It says what? When evaluating the velocity of an object, one must keep track of direction. The direction of the velocity vector is the same as the direction which an object is moving. It would not matter whether the object is speeding up or slowing down. For example, if an object is moving rightwards, then its velocity is described as being rightwards. Boeing 747 moving towards the west with a speed 260 meters per second has a velocity of 2 meters per second west in that same direction. Okay, but so you can see that the speed and velocity in this case are the same, but immediately there is a change in direction. Of course, the velocity itself will change instantly. Okay, I've discussed about instantaneous velocity. the speed at an instant is known as the instantaneous velocity. And how would you obtain the average speed? The average speed of entire journey could be calculated as the total distance traveled over the total time taken. That the ratio of the total distance traveled to the ratio of the total time taken. Then acceleration. Now, describing speed, we have two physical quantities that is used to describe speed. And what are those physical quantities? We have distance and time. Then to describe velocity, we have displacement and time. Then to describe acceleration, we have velocity and time. All of them, what is common is that they are all with respect to time. Speed, distance, velocity, displacement. Acceleration, that is velocity, change in velocity with time, rate of change in velocity with time. But then the acceleration we have is classified to, we have the negative acceleration, positive acceleration and negative acceleration. For the positive acceleration, there is an increase in the rate of change of velocity with time, and increase in the rate of change of velocity. Okay, but for negative acceleration, which we also refer as deceleration, there is a decrease in the change in the velocity with time. And what is the unit is the SI unit is meter per second square. General formula is change in velocity with change in time. A very important formula we have here when it comes to the derivation of equation of motion. Okay. Okay, looking at this particular table we have here, it tells us that here the time here is 0 and here the velocity is 0. The velocity here 10, time 1, 20, 2. Okay, now looking at this now, what is the interval, the change in velocity here? The interval here is 10, here is 10, 10, and look at the interval of time as well, the same interval all through. So what does this simply mean? It means that this is the table of of a uniform acceleration. But if we are having the difference or the change in velocity is not at equal time interval, then we'll be having a non-uniform acceleration. Of course, a uniform acceleration definitely is going to give us for the velocity time graph will give us a straight line, a linear graph. In fact, all uniform motion, uniform speed, uniform velocity, uniform acceleration, their graphs are always uniform. That is a straight line graph. Okay, but for the non-uniform, you don't have a straight line graph. Okay. Now let's now move to equations of motion. Equations of motion, but then with a constant acceleration. Okay, a car moves from a particular point. The driver steps his foot on his accelerator or the throttle, and the car starts moving with a constant acceleration. Okay, so these are equations of motion with constant acceleration. Okay, the first one is v equal to u plus at. The next one, s equal u plus v over 2, all into t. We have v squared equal u squared plus 2as. We have s equal ut plus half at squared. All right. So one important thing you should know is how to derive this equation. How come these equations? Okay, and first you should know the variables, what each of these letters stands for. Then after which you should be able to know how they are being derived. So let us begin with the variables. There are 5 variables. The first one is the initial velocity. Okay, next is the final displacement. T stands for the time it moves from initial velocity to final velocity. Then A, constant or uniform acceleration. Remember, this equation is basically for constant acceleration. A body moving from one point with the initial velocity, okay, then the acceleration moving steadily, a constant acceleration to attain another velocity. So how then do we come about this equation? Okay, remember this equation will also lead us into the horizontal linear and the vertical linear. For the vertical linear, you're talking about the vertical motion under gravity, but this is linear, the horizontal motion. Okay, they are used in the same way, but some little changes which we are going to discuss when we produce that video in that vertical dimension. Okay, acceleration is the time rate of increase in velocity or change in velocity. Okay, so this is how we start it. Acceleration is the time rate of change in velocity. So you need to know this definition. Acceleration is equal to change in velocity over time. So what is this change? What is that change? You have to velocity, final, initial. So when you subtract it, you get that is the change, v minus what u all over t. Change in velocity over time. So from here, we now make v the solid of the formula for us to have v equal what? U plus at. So this is the first equation, equation 1, v equal u plus at. Now the next one, average velocity, okay, which is what? The displacement over time. Displacement is the s, represented with the letter s, time with the letter what? T. Then average, how do you obtain your average? You have your two velocities, initial and the final, add them up and divide by what? 2. So this is the average velocity, v plus u plus v over 2 equal your displacement s over t. So you have this. Then with this, what then do you do? Let's now make s the solid of the formula. Making s the solid of the formula, what do we have? We have what? S. So when you make s of the formula, of course you are going to have what? S equal what? U plus v over 2 all into bracket what? T. Okay, my t is missing here. U plus v over 2 into what? T. My t is missing here. Okay, that's what I have here. S equal to what? V plus u all over 2 into what? T. So now, how then can we obtain the next equation? Okay, so if we now substitute this equation, v equal u plus at, we now plug it into s equal v plus u all over 2 into what? T. We plug the v is what? U plus at. When you plug it in here, u plus u is 2u times t, 2ut, at times t is 80 squared all over what? 2. Okay, this is it, 2ut plus 80 squared. When you use t to open up the bracket, okay, all over 2. Then you cross multiply, 2s equal with 2ut plus 80 squared. Divide all through by 2, then your final equation here is what? S equal to ut plus half at squared. Now, how then do we obtain the next equation? The next equation, which is v squared equal to u squared plus 2as, we go straight to this first equation which we had here, v equal u plus at. Make t the solid of the formula. When you make t solid of the formula, of course you are going to have t equal v minus u all over a. T equal v minus u all over a. Let us get it right here. Okay, this is it. From equation 1, make t the solid of the formula. So this t is equal v minus u all over a. So what then do? We plug it into s equal v plus u over 2 all into t. Listen, the two equations are being substituted into this particular one we have here, s equal v plus u all over 2 all into t. This is a way of you to remember. The two equations obtained from what? The first, from the definition of acceleration, that is v equal to u plus at. Then from that v equal to u plus at, I make t sort of the formula to give me what? V minus u all over a. Both, okay, are substituted into s equal v plus u all over 2 all bracket what? Into t. Based on what you want to derive, you should be able to know which of them you are going to plug into s equal v plus u all over 2 all bracket t. So the other two, this other one, then the other one, v equal to u plus 80, they are all plugged into this. So when you plug this into here, when you substitute into this end, you now have what? V plus u all over 2 into v minus u all over a. Oh, okay, the top one is multiply v plus u in bracket, v minus u in bracket, 2a. So what I have here is difference between 2 squared. So if you expand it, that is v times v squared, v times u minus vu, u times v plus uv, then u times u minus u. Then when you resolve it, you have your v squared minus u squared equal to what? 2as when I cross multiply. Then let's make v squared sort of the formula. Then finally have what? This. So you should be able or learn how to do what? Derive these equations. Then the next one is application. How do we use this equation? It's very, very important. Now, one thing you need to know is that if you look at these equations we have here, the equations of motions. Now, these equations, each of the equations have 4 variables. Each of them has 4 variables, each of them. Okay, so you'll be most likely you'll be given 3 values of the values of 3 variables, and you'll be asked to find the 4th one. So if you look at them, they all have 4 variables. Look at these 4 variables: 1, 2, 3, 4. Speed, initial velocity, final velocity, time. Here you have final velocity, initial velocity, acceleration, displacement, initial velocity, time, acceleration. 4 in each case. So we'll be given the value for 3 and be asked to find one. So let us take some examples. Now the first example we take is this. A truck starts from rest. When an object starts from rest, what does it mean? It means that its initial velocity is what? Is 0. So we have the first parameters here, which is u equal what? 0. A truck starts from rest and moves with a constant acceleration a 5 meters per second square for t time 20 seconds. Okay, so these are the parameters which I have. That is the first thing you need to do. Write out the parameters. It will give you an idea of the formula to make use of. So we have the initial velocity, we have the time, and we have the acceleration. So we are looking for the velocity v. So which formula consists of v, u, t, a? Of course, it is v equal to u plus at. So keep all these figures to replace their variables. We have this, and at the long run, our answer gives us what? 100 meters per second. Then to determine the distance it traveled, we have s equal what? V plus u all over 2 into what? T. So at the long run, we now solve and we now have this. But then we can see this equation as well. We have distance, we have initial velocity, we have time, we have that. Okay, do we have the acceleration? Okay, before we make use of this, yes, we have the acceleration a, the acceleration 5, we have it. Then we have our time, so we can make use of this formula, and we still have the same answer. So that shows a clear understanding of the use of the equation. Then number 2, it says that a car traveling on an expressway decreases its speed to what? To 12 meters per second in 3 seconds. If the car if the car has a total distance of what? 60 meters during this time, calculate 1, the initial velocity of the car, 2, car's average retardation. Okay, if the car's total distance of 60 meters during this time, calculate what? 1, the total internal initial velocity of the car, then 2, car's average retardation. So what are the parameters given? We have what? A car traveling on an expressway decreases its speed to. So that means that this velocity is my final velocity. So now we are asked to look for the initial velocity. We have the time, which is 3 seconds, and the distance is 6. So from this 1, 2, 3 parameters are given, so we are looking for u. So which equation has all these included? So it is s equal v plus u all over 2 into what? T. Plug in or key in those variables in this equation, we finally have this. Solving at the end, we now have 28 meters per second. Okay, how do we solve this? Is 60, 26 plus this one, open the bracket, cross multiply 60 times 2, 120 equal 36 plus what? 3u. Take this one over, we have 120 minus 36 equal to 3u. Then you divide both sides by 3. Our final answer is this. That is that. So the next one is for the Car's average retardation. For the Car's average retardation, we have, okay, we are looking for the retardation, which is A. This is meant to be A and not U. S equal what? UT plus half A. Please take note, this is A. Okay, A and not U. Okay, UT plus half AT squared. So let us substitute. By 60, initial velocity is 28, T is 3, then I have half, then my A, okay, this is A, which is what I'm looking for, and the time is 3. 3 raised to power 2 is what? 9. Alright? So 60 here gives me what? 84 plus 9A. 1 times 9A is 9A all over 2. Take this over, have 60 minus 84 equal 9A all over what? 2. Okay? When I subtract, I will have minus 24 equal 9A all over 2. Then cross multiply, minus 48 equal 9A. Divide both sides by 9. I have this. A is equal to what? Minus 5.8 meter per second squared. So acceleration equal minus. So when they say your acceleration is equal negative 5.3, meaning that what the negative tells you that it is deceleration or retardation. But if you want to present your answer in this form, deceleration, there's no need to put in the what? Negative sign again, because you have made us know that it is deceleration. But in this case, A can stand for acceleration, A can stand for deceleration. But what we distinguish them is the sign here. If you have a positive sign, that means it is acceleration. But if you have a negative sign, it means that it is what? Deceleration or retardation. So at this point now, we are done with this, and I expect you all to look into this activity on your own, go through it, and then see what you can come up with them. All right. So at this point, I will draw the curtain for today's class until we have another contact again. My name is Mr. Uche once again. May God bless you all. Thank you.